Alright, we did a good job with area here today. Now we're ready to tackle volume, and specifically with volume, there's two main categories. We could do volume by revolution, and then there's also volume with known cross sections, and two quite different ideas, but with a lot of similarities with regards to calculus. Now, when we do revolution, we always have to make that decision right off the bat. Am I creating a disk when I revolve this object, or am I creating a washer? Okay, slight difference here, and we'll take a look at both of them tonight. Now, as far as graphics, I found a few cool graphics to help illustrate the washer, so you can kind of visualize what you're accomplishing and not getting lost just in the number crunching. But over here, we're going to start with this two-dimensional image, and we're focusing on the region that's bounded in the first quadrant by radical x, the vertical line x equals 4, and of course the x-axis. And what we're going to do with that is we're going to revolve it around the line. It looks like y equals -1 right here. And they've already got the cross-section, or this rectangle, drawn in there for you. How nice. And what we're going to do is we're going to start to revolve this orange shape around that axis, and over here is that three-dimensional image that you're going to get, and sometimes it's very hard to visualize, but it kind of looks like a bullet almost, kind of a bullet-like image. We also found, to go along with that, kind of a cut in half slice, so you can kind of see inside, and the emphasis is you do have that hole, you do have that hole in the middle. And right in here you've got the hole, so we have to account for that hole when we go to find the volume, knowing that there is empty space in the middle. And here's the image that I really want to take a look at, and that's, we had that rectangular slice drawn on the original picture, and here's what happens if you just revolve that one thin rectangular slice around the line y equals -1. So what we're going to do is we're going to find the area of this washer, and we're going to call that the outer radius. And then we've got inside here, we've got our inner radius. And so the area of this one little itty bitty slice is going to be pi times capital R squared minus pi times little r squared. And by subtracting the little circle out of the big one, you're left with just the area of the washer. Now, of course, the calculus says if you want to add all those rascals up, we're going to factor out our GCF of pi. We've got our integral from a to b. And then we've got our capital R squared minus our little r squared with respect to x in this particular case. And I just want to emphasize that we are squaring each radius individually here. Now the only difference with the disk is that you will have this hole filled in. Therefore, you do not have an out or a little radius on in the inside, and so if this one was washer, then we could say the disk is much simpler. It just says, hey, we just need one radius and square it, and we're done. Now, I personally find the ones with known cross-sections easier to do calculus-wise, but harder to visualize. And so I found a couple of pictures. There's not many good ones out there, but I tried to import a couple of decent-looking ones. Now, on these first two pictures, they have the same base region. And I think if you look real closely, it looked like to me that it was something like y equals x squared minus 1, and maybe something like y equals x plus 1 was so it kind of had like a parabolar base right here, and then you could see that linear outline right there, and then on top of that region we're going to implant these squares that are coming out of the region at us like a hologram almost. And so this one's got square cross sections, creates quite the interesting object, and then this one over here looks like it's got rectangular cross sections. Now the two examples down here, they have a circular base. Looks like to me maybe x squared plus y squared equals 2 is that circular base that runs around there. And then, of course, this first one, I can't tell for sure, but it looks like they might be square cross-sections. You can make the argument that maybe they're rectangular, doesn't matter. But then over here, we've got equilateral triangles, and those are extra interesting ones. And I think it's pretty neat to look at the shapes they created and try to visualize them. The big emphasis here that I want to see from you guys, just to ensure the accuracy of our solutions, is we do want to put an emphasis on our slice analysis. Just like the projects we made in class, the beautiful ones that are hanging all around the room. We've got, for instance, if you were doing a square, you've got your base, you've got your height, you've got your area of that one slice, and then you've got the volume of the entire project. If you were doing a semicircle, this one's pretty interesting. what you're going to end up with is you're going to start with the diameter, and then you've got your radius, and then you've got the area of that one slice is going to be 1/2 pi times your radius squared. Now, by the time you're done, it actually turns out to be 1/8 pi times the diameter squared every time. And then, of course, you got your volume after that. You can go to town with that one. Now, as far as the equilateral triangle goes, I think that's by far the most challenging one. Okay, you've got your base, and then you can get your height, and then the area of that one slice. Now, actually, what it turned out to be, and this is kind of a tough one, it's actually radical 3/4 times the base squared every time. And then, of course, you can go to your volume. Now, how did I get such an interesting formula for area? And you can refer back to your notebook, and I won't bore you with all the details here, but we had an equilateral triangle where all the angles were 60, and we said, okay, we're going to draw a right triangle, and if I focus on just this right portion here, we've got half the base here, we've got our height here, and then we said that the tangent of 60 was equal to the height divided by 1/2 of the base, and then we solved that to get the height in terms of the base, and then we came up with this really cool formula over here. So I usually don't memorize this formula personally myself, but what I do, if I ever, once every 5 years when I see a problem on equilateral triangles, I draw this picture and solve it that way. Alright, the big trend we've seen the last couple of years is the AP's tendency to make these volume questions a non-calculator question. So either they're going to give you something where they ask for setup only, or they give you something that's very easy to integrate by hand and very friendly number-wise. But I want you to consider the region bounded by y equals 3 radical x, the region, or the line y equals 6, and then also the y-axis x equals 0. So first things first, let's see how good of a drawing we can generate here. Alright, we know what radical x looks like, so 3 times radical x is just a taller, steeper function. Let's see, y equals 6 is going to run right along there. Alright, and let's find that intersection point. All we're going to do, time out, I want to shade in first. They're describing the region bounded in this neck of the woods right here. So we got that shaded in. Now, as far as the intersection point goes, we're just going to set the functions equal to each other, and we'll divide the 3 over, square both sides. I got x equals 4, so that intersection point right there corresponds to 4 on the x-axis. Okay, I think we got ourselves a great drawing. If we integrate with respect to x, it's going to be 0 to 4, and if we integrate with respect to y, it'll be 0 to 6. So let's jump into one here. I want to revolve this rascal around the line y equals 6. Can we do that? Let's find the volume of the solid generated when we revolve it around the line y equals 6. So here's what's happening. Let's see if we get ourselves a good rectangular slice here. Here's my slice, nice skinny rectangular slice. And if I'm going to say that is touching the axis of rotation, so I've got a disk. And this says you only need one radius, and that's going to be the length of the slice itself. And to get the length of that slice, it's strictly upper minus lower. So I'm going to say pi times the integral from 0 to 6. My one radius is upper minus lower quantity squared dx. Alright, now here's my challenge to you. I'm not going to go any further with this one in part A. But what I want you to do in your notebook before you come into class tomorrow is to work this one out by hand, strictly by hand. I want you to do the foiling, I want you to do the integrating, and I want you to plug in those bounds by hand. Whoops, I almost led you astray. The upper bound should be a 4. Hopefully you were kind of scratching your head on that one. And one of the first things we do in class tomorrow is I will check your numerical answer and the work behind that tomorrow. So I'm going to leave that for you just to make sure you can do it by hand. And then we're ready for part B. For part B, I want to now revolve that same region around the line y equals 10. And this one we're going to do setup only. So let's go back and take a look at that picture. The line y equals 10 is clearly above the region. We'll say it's up here somewhere. And now my axis, or my rectangular slice, is not touching the axis of rotation. We've got that gap in the middle, so I'm going to say we've got ourselves a washer. My outer radius is there. My inner radius is right there. Outer is going to be 10 minus 3 radical x. Inner is going to be 10 minus 6, which turns into a 4. So let's go see if we can square both of those individually and set this up. All right, pi, integral from 0 to 4 again. Outer radius, 10 minus 3 radical x quantity squared minus 10 minus 6 quantity squared with respect to x, and boom, that's all we were looking for there. Now for part C, our last part for this particular question. It's very wordy, but we're going to sort through it and make it look like a really easy question, and hopefully you catch the big bear trap right off the bat. But they said, all right, consider the region R as the base of a solid where all the y's range from 0 to 6. Now the cross sections of the solids taken perpendicular to the what? Yes, the y-axis. As soon as they said perpendicular to the y-axis, you started thinking horizontal slices, right? And some of you may have a moment of panic, but we just need to make sure everything's in terms of y, not only the bounds, but also, the functions themselves. And they also said the height's 3 times the length. So when we go through our slice analysis, that'll be really important. Let's go back up here and take a look at this picture. Okay, now the slices are perpendicular to the y-axis. So let me get a new color here. So I'm picturing a slice that looks like this. Perpendicular there. And the length of that slice, well, I've got to find this new function. Instead of saying y equals 3 radical x, let's say y squared over 9 equals x. How about that? So just solving for x. So the length of that slice is just going to be y squared divided by 9, right there. And that's all we've got to worry about. So let's go take a look at our setup here. So our slice analysis. Now, the base, we said, is going to be y squared divided by 9. The height's going to be 3 times that size. You could simplify it if you want. I'm not too worried about it. The area is going to be 3 times y squared over 9 squared. And so the volume, check these bounds out. We're going from 0 to 6 because the lowest y value and the highest y value. And we've got 3 and then a quantity y squared over 9 squared with respect to y. Now, notice there is no pi in this one. Definitely no pi. And I think it's very easy to assume. We could work this one out if we had to. I'm not going to ask you to do so. I just want you to work on part A for tonight. All right, our last one for the night, I want you to be calculator active. Grab your calculator. I'm going to have you do a lot of the work on your own. And I want this to be very interactive. And let's not get too passive and just sit back and sit in cruise control. Grab that calculator and get ready to rock and roll. I want you to consider the region bounded by the natural log of x, also y equals 6 minus x, and the line y equals 0. So we're sitting up in the first quadrant. Hit the pause button, take a moment, and generate this picture, and certainly feel free to do this one by hand. I think you can come up with a good picture by hand, but also throw it in your calculator, try to create the good window, and then we're going to go get those intersection points. So here's how I'd start off my problem before I even got to part A. I'm going to let the grader know that I set these two functions equal to each other and that they intersected at an ordered pair that I'm going to call A comma B. And so I'm storing the x value of 4.4, 9, yada, yada, yada. I'm going to write down every decimal that I see, comma 1.503, and yada, yada, yada. And I'm just writing down all the decimals I see on my screen. I'm letting the grader know that the x value is stored in A and that the y value is stored in B because I'm going to likely use both of them here in this problem. The first thing I want to do is think about if they wanted the area of this region, would you do it vertically or horizontally? Okay, if you do it vertically, how many integrals do you need? How many do you need? Well, hopefully you recognize that if you do it vertically in terms of x, you're going to need two slices, one that's bounded on top by ln and then one that's bounded on top by the linear. By comparison, if you did a horizontal slice, you can do it in just one integral. And so that's what I'm going to go ahead and do. If I want the area of that region, I'm going to strictly do the integral from 0 to alpha b. I'm going to do, let's see, 6 minus y minus e to the y dy. And that would give me the area in one integral instead of two. I think it's quicker, I think it's more efficient, and it's certainly going to give us the right answer. Now check out this part B that I want to throw at you. Now they're going to say that a horizontal line, not a vertical but a horizontal line, y equals k, divides this region into two regions of equal area. Right, but do not solve an equation involving one or more integrals whose solution gives the value of k. So here's what I'm thinking. I'm visualizing a horizontal line, and it's probably pretty close to where I have my red line, except, should be a little higher, wouldn't you say? So I'm picturing maybe some very faint line K, right around there, maybe a little lower. It's going to split it in half, and so here's what I'm thinking. They said we could do one or more integrals. Let's do it this way. Let's say we already found the area of the whole region, and I'm not sure what it is. I actually haven't typed it in yet myself. Let's call the area of the entire region C. So now what I could do for the part B here is I say, let's integrate from 0 up to K. That same region, right minus left, and set that equal to 1/2 of C. Or the other option is to integrate from 0 to K and set that equal to the integral from K to B. Same region. And this would also earn you full credit on a question like that. Now you're sitting there wondering, why are we talking about so much about area? This is a volume night, and it is. So let's go ahead and revolve that region around the line x equals -1. Let's go take a look at our drawing, see how that pertains. Let's see, x equals -1 would be over here, and so we've got definitely have a washer. I'm going to use the red line as my slice, and I'm going to say my outer radius is that length. That's, again, I'm going to do right minus left. My inner radius is right here, right minus left. Everything's going to be in terms of y, and we're going to integrate from 0 to b. So let's go set this up. And I'm going to do, let's see, okay, 0 to b, outer radius, right minus left. So let's say the linear function 6 minus y minus a -1. So we could certainly clean that up. I'm going a little bit overkill. The inner radius is e to the y minus -1 squared. Make sure we got squared on each of those. Good, 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 good. All right, the last one here, I want to revolve that same region around the line x equals 8, and you guys are going to do setup only on your own, and that's going to be the second thing I check in your notebook. So the first thing is we got to go back to the last problem, and we got to work out that one integral by hand. And then you're going to come over here and you're going to do setup only, revolve it around the line x equals 8. And I think that's going to be a really good one to test us on. So I'll check you guys tomorrow and see those notebooks.